Hello. Now we are going to look at the different shapes that we can get from our histograms. So the distributions of our data, if we draw them on a histogram, can have different shapes. So we're going to look at the different shapes of histograms and what that can tell us about the data we are looking at. So I have this drawn as a histogram, as we would be used to, and then this is a more continuous version of a histogram that will be important later. So effectively, what brings you from a situation like this to a more smooth looking curve is that you break these bars up into finer and finer widths. So you break your intervals, your classes in your histogram into finer and finer intervals, smaller and smaller intervals, and they will form this more continuous curve where effectively the bars are thin enough that you start to end up with a smooth looking top to our tops of our bars, and you just draw the tops of the bars in and you end up with something that looks like a smooth curve. That's where these smooth versions of the histograms are coming from. Now, let's jump into our different types. The first one is symmetric. So symmetry is a word we know well in maths. Effectively, one side of something is going to be mirrored to another, or you could fold one side onto another. So you can see in a symmetric data set that our mirror line, our symmetry line, is right down the middle. We could fold this shape over or pretty well onto itself. So it is symmetric. It is mirrored down the middle. In that type of situation, the mean, the mode, and the median are all in the same place. They all have the same value. They would all be coming down right down the middle. These types of graphs will be very important as we move forward. And part of the reason is that because when we take random samples of large populations of height or weight or IQ, we end up with this type of symmetric graph where we have most people around the mean, mode and median, and then we have a fairly predictable falling off of people who are much taller or much shorter or so on. Now, the next piece is really just to get used to language. If you have data that we say is positively skewed, the easiest way I find to remember this is that skew is a name for a wedge. That's what the word skew means. So you have a wedge pointing out in the positive direction for positively skewed data. And for negatively skewed data, you have the wedge pointing out in the negative direction. So that is really all we need to be able to get from the name. But what does it mean in practice for our mean, our mode, and our median? Well, we know that the mode is just the most frequently seen thing, and we know the frequency of our histogram is going on our y-axis, our up and down axis. So the mode is always the top of the hill. It was the top of the hill here, it's the top of the hill here, it's the top of the hill here. It will always be the top of the hill. It's very easy to remember. What we have to think about with the mean and the median is what was the problem that we always identified with the mean? It was that it was heavily affected or very affected by outliers. And what's happening with our skewed data is we have not a non-zero, a non-insignificant number of people who are very much outside of the main group. So we have these group of outliers that's going to heavily affect the mean. So our mu symbol is for our mean. And it's going to pull it up towards those outliers. If we have people who are, so we have the age at which people first speak. So as babies, when do our babies start to speak first? A whole bunch of them are going to do it at a particular time, and then some people are going to be later. They'll start speaking later. And these people who speak a lot later, start speaking a lot later than the main group, are our outliers, and they're going to pull up the mean age at which people speak a lot. The mode obviously won't be affected at all. It's just what age is most common for people to speak at. And then the median gets affected a little bit because we know that these people would still be in our list. They'd be at the top end of our list and they'd pull the median value up a little. But the easiest way to remember, mode at the top of the hill, mean is going to be very affected by outliers, and then median will sit somewhere in the middle. The same type of thing happens for our negative skew, just that the mean is now being pulled down towards these smaller outliers as opposed to the bigger outliers before. And an example of negatively skewed data, again, where the wedge is pointing in the negative direction, would be where we had the heights of professional basketball players, where most of the people involved are going to be very tall. So the mode is going to be very tall, and we don't have very many short professional basketball players. Now, uniform data comes up from time to time. It's an example of a type of symmetric data, but it's where all of the outcomes come up equally often. The mean just sits in the middle, and the only thing to really think about it for the uniform distribution is it has no mode. All of them are equally seen as often, so there is no mode to that data set. In contrast to our symmetric situation, we could have, or to any of other situations, we could have bimodal data, or technically multimodal data. So if there are obvious bars that are roughly the same height or the same height, then we would say that we had more than one mode. Obviously, at a certain point, it stops being sensible to talk about having modes. We get towards the uniform situation. But in a situation like here, where we have two bars that are obviously jutting out to basically the same height above the rest of the data set, we would say that both of those would be our modal intervals. They would, whatever the values we've got here, they would be the modes of our data set. And then finally, we have to think about what would standard deviation look like when we're looking at histograms, when we're looking at distributions. Well, we know that the standard deviation is the average difference between the mean and all of the points in our data set. So effectively what we're looking for with standard deviation, to make a judgment about standard deviation, is if we can see roughly where our mean of our data should be, so centered as well as we can judge based on the frequencies. How spread out is our data going to be away from that mean? If our data is very spread out, that's going to give us a large standard deviation, because the difference between a value down here and our mean is going to have a big effect. But because there's only a small amount of data far away from our mean here, we would end up with a relatively small standard deviation. Whereas if we had this relatively spread out data set, it's not that it's massively wider, but there's no concentration of data near the mean. So you could have data that is very wide ranging, but you could also just have data that doesn't have a concentration near the center of the data set, near the mean of the data set. And that would mean that on average, your differences from your mean out to your data points is going to end up being bigger, and that is effectively what our standard deviation represents. So when we're trying to make a judgment about standard deviation, we're saying, well, how spread out away from our mean is the majority of our data? And if it's very spread out, we have a big standard deviation, a big average difference. And then if it's quite concentrated, we have a small standard deviation, a small difference on average from our mean to our data points. And that is what we need for the shapes of our distributions.